Hey guys, welcome back. I'm going to try and finish chapter 6 here today in the notes, but here we go. Jokes. I'm just looking. Here's one. What do penguins use for napkins? Flapkins. You're probably saying that's not very good, and you'd probably be right. Okay, so what we're going to do is we're going to pick up where we left off. We were talking about Hess's law. We're just going to do one more example, and there's one other way to do to solve for delta H in this chapter, and I want to talk about that, and that comes from table values. But first of all, back to where we left off. So we talked about Hess's law, and so just rewinding here a second. So we did this problem in class, okay, and they'll never use the word Hess's law, but if a problem gives you a series of reactions like this one did, and I'm going to do another one here in a second, again, you're going to have to reverse them or change the coefficients to get them to sum the total reaction. Okay, so here's the next example. Okay, and what's on the top is the target reaction. That's what we want to get these reactions to total up to. Okay, so you guys can look for this online. Okay, so I've written this on the board. Okay, so let me move over here and make sure that you guys can see this. Okay, so this is that reaction. We're trying to solve for delta H. The way they put it is they said determine the delta H for the following reaction. This one's a little tricky, and I don't think I do anything like this on a quiz or a test. But again, if I want to get to this reaction, so I want to get these, almost always every reaction is going to be used. But this time, there's not, and I'll show you that. So again, I want to total these up. So I start off by looking here. It's carbon graphite. This is the target. This is what I'm trying to work towards, is this reaction right here. And so in this first reaction, I see that. So I'm not going to change that reaction at all. The next thing, and I see the 2H2 and the half O2, but the other thing is this little bit bigger thing that doesn't come up as often, CH3OH. And I'm going to look at that. And I see that in this third reaction. And I see it where in the target reaction, it's on the right, where here it's on the left. So I'm going to need to take this and reverse it. So I get CH3OH on the right. So I'm just going to reverse that reaction. Remember, when I do that, I change the delta H. So when I do that now, I flipped it. So now I have CO2 gas plus 2 H2O liquid makes CH3OH liquid plus 3 halves O2 gas. And now I'm going to change the sign. So now it's going to go from what it was negative to positive. So I did that. So now I'm taking care of this and this. And like I said, this problem is one that is confusing in that you don't use all these reactions, and usually you do. So maybe if you guys take chemistry beyond our class, they would do this. I don't think I do this on any quiz or test. The third reaction here, you don't need. And so I'm just going to take it out. So I'm just going to take out this reaction. It's kind of an evil, mean thing to do. So now if I total this up, and let me see if I'm ready to total it up yet. I'm not sure. So for H2's 2 on the left, and I only see 1 here. So I know that I need to get 2. So I'm going to have to double everything here. So 2 becomes 1, becomes 2. And so this I'm going to double. So I'm going to multiply by 2. And when I do that, so I have 285.2 times 2 gives me negative 571. Okay, again, so I took that out. Okay, so now I think, and then the half O2. So let me just see what happens here. So I've got the C, I've got the carbon graphite. I've got the two H2s. Now for O2s, I've got 1 plus 1 is 2. But here I have 3 halves, and so that's going to go away, and this is going to go away, and I'm going to be left with 0.5. I'm good, and then there's CH3OH. So again, it's really like a puzzle. It's just flipping things around. And then to solve for delta H, I'm just going to add this up. So I'm going to take negative 393.5 plus negative 571 plus negative or a positive 726.4. I'm going to make sure of this. So this is the delta H for the whole reaction. I have it as negative 238.7 kilojoules. So let me just check my math. Negative 393.5 plus negative 571 plus 726.4. Yep, negative 238. I have negative 238.1. Let me do that one more time. Negative 393.5 plus negative 571 plus 726.4. Yep, negative 238.1. And this is the kind of thing where if you look at it, you go, oh, I got that, I understand that. But then in the actual doing it, you've gotta you got to really go through the process and do that. And that's why what I'm saying is you really need to do some practice on these. Okay, and then so that is Hess's law. So that's the third way to solve for delta H, guaranteed on the quiz and on the test. And it's not a huge amount, but it is going to be on there. Okay, now the final thing, the final way to solve for delta H, and again, I don't think it's a difficult process, but this is where we use table values. Okay, note too, there's problems. It would be good to be working problems in the book. Okay, now the fourth method of determining delta H from a reaction is the standard enthalpy of formation. And this is where you are going to be given tables from you're going to be getting values from a table. So that superscript 0 just means standard state, and you can see what standard state, it's kind of like STP but different conditions. So standard state is 1 atmosphere pressure, it's a pure liquid or solid, and solutions are 1 molar. And then the F just means a formation. So in other words, and I'll show you here in a second what I'm talking about with formation, just the elements that the compound is made up of that they react with. So define the change in enthalpy that accompanies the formation of 1 mole of a substance from its elements at standard state. And so what I have here on the left, I would always give you, and you'll see, we'll do a couple problems like this. Okay, and then this equation here, and again, you're going to see you're going to have to be given table values to do this. But this equation here on the bottom of this slide is stuff that is on the formula sheet. I know you can't see me very well, but if you look on the formula sheet, it is right down there. So it's on the formula sheet, and it's always in those Greek letters mean the sum of. So the sum of the delta H of the products minus the sum of the delta H of the reactants. And so the only thing that's confusing here is you just got to remember you do products minus reactants. Okay. So now we're going to, first of all, I want to make sure you understand what this means, this standard, the formation here. So write an equation that produces H2O from its elements. So what is the delta H for this reaction? So if I do that, sorry guys. I always screw up. Okay, so if I do that, I want to write water from its reactants. So all I would do, I'm doing it right here. So I'm just going to do H. I know that water is made up of is hydrogen and oxygen, and both of them are diatomic. Then I just balance the equation, and so to do that, I need a 2 here and a 2 here. And actually, the way we want to do this, let me I want to do this in defining in 1 mole of water. So if I do that, I'm going to put a 0.5 here. So 2 H's, 1 O. And then the delta H, so this is so when it writes this, the delta H, this means standard state. That's what I was talking about. Standard state is 1 atmosphere pressure, a pure solid or liquid, or if it's a solution, 1 molar. And the F is the formation. That's what this is. This is the formation of water. And then the delta H was right in the table. It was given there in the table, and it was negative 286 kilojoules. Okay, so that's how to do that. Now the next one, same exact principle, just this whole thing about the formation. Okay, so now here's the next one. So write an equation that produces CH3OH, so that's called methanol from its elements. And see, you're given the value, it's covered up there, but it's negative 239. It's the second one from the bottom. Okay, so if I do this now, and I always want it to be in terms of 1 mole of that CH3OH. So here I would have carbon, which is not diatomic, plus hydrogen, which is diatomic, oxygen, which is diatomic, and see we're making what we're trying to make here is this. Okay, so I have the carbon, and I'm just showing the formation of this from its elements. And then if I go back and balance, I put a 2 here, and I would put a 0.5 there, so 1 carbon, 4 H's, 1 O, and then the delta H again was right in that table. And the units are important here. This is kilojoules. And even going back to this problem that I did a few minutes ago, this problem right here, the answer, I can get this on my screen, the final answer was in kilojoules. Remember, some of those we did with calorimetry were in kilojoules per mole. Okay, so that just to kind of make the point about what the formation is. Okay, and then now to do these problems, which again, I don't think are difficult problems, but it's problems that you really just need to do a couple of them to make sure you're good. Okay, so here you'd have to be given the table values. Okay, so we're calculating delta H using the addition of the heat of formation. So in other words, you have to be given the values again from the table. Okay, to do these. Okay, so if I do this, okay, and first of all, so if we went to a table, so the delta H of the formation, and again, this is actually in the back of our book. So if you were to go to the back of the book, you'd see this. So CH4, you kind of got to watch the units here. You always do. Is 75 or is negative 75 kilojoules per mole. O2, whenever you have an element by itself, it's 0. Okay, and then the CO2 is negative 393.5 kilojoules per mole. And then the H2O gas is negative 242 kilojoules per mole. So this you could either look up on a table or you would be given that. So you'd be given that. So here was our reaction. So I have CH4 gas plus 2O2 gas, CO2 gas plus 2H2O gas. Okay, so if I'm given the table values, what I'm going to do is use this. So I want to solve for the delta H. I'm going to do the delta H of the products minus the delta H of the reactants. Products minus reactants. Remember, the products are here. Reactants are here. Okay, so watch how the units work. Okay, I'm going to have to right over here. So the delta H, so the product, so I've got CO2 and I've got 1 mole. So it's going to look like this. So I've got 1 mole of CO2, and CO2's value, which I have to be given, is negative 393.5. The 1 is because the coefficient was a 1. So times negative 393.5 kilojoules per mole. So what happens here is the moles cancel out. So that's the CO2, and then I'm going to do the H2O. So this time, because it's got a coefficient of 2, I'm going to do 2 moles of CO2, and the value, or I'm sorry, for H2O is negative 242 kilojoules per mole. So the moles will cancel out. So there's the products. Okay, now I'm going to do the reactants. So I've got, again, because the coefficient is 1, so I have 1 mole of CH4, and then I'm going to multiply. CH4 is negative 75 kilojoules per mole. And then O2 is 0. So my units here will be in kilojoules. So again, you kind of just got to make sure, again, you look up the values. Usually I give them to you, but in the book you have to go look them up in the book. Make sure the coefficients are the moles. Make sure you do the products and then you do the reactants. And what I end up getting here for delta H is negative 1,124 kilojoules. So this is an exothermic reaction. It's always kind of good to go back and ask yourself, does that make sense that that is an exothermic reaction? And the answer does make sense, because we know that when we light a Bunsen burner, it gives off energy. Okay, so let me show you another one of these. Okay, so here's one, and this is actually would be a great problem to, or here's one. I'm sorry, I'm getting ahead of myself. Okay, so calculate the delta H for this reaction. Okay, so let's again go through this reaction. And again, so you guys could go again to the back of the book. And I actually made a mistake. I made a mistake here. So I'm sorry, guys. I was looking at the wrong problem. Make sure I got this right. Negative 242, negative 75. The answer I have is wrong. The answer I have is wrong. Please, hopefully you followed along. The answer here was negative 802.5 kilojoules. The sign's important. So note that the answer to the methane one, CH4, was negative 802.5. Okay, so again, note that that was an error. Okay, so now this was the next problem. Okay, so here again, so this is the reaction we're dealing with now. So we're trying to solve for delta H. So I've got 2 H2S gas plus 3 O2 gas equals 2 H2O liquid plus 2 SO2 gas. Okay, now here, so we've got, so let me give you the values here. So again, these you could look up in the back, the appendix, the back of the book. So the H2S gas is negative 21 kilojoules per mole. The O2, again, is going to be 0. Something by itself is 0. H2O liquid is negative 286 kilojoules per mole. Okay, and then SO2 gas is negative 297 kilojoules. So again, these values you could look up or they would be given to you. Okay, so now, again, just so we're going to do, we want to solve for delta H. So delta H is the H of the products minus the H of the reactants. So I'm going to start here, so I'm going to write it all the way over here. And again, so I'm going to start on the right. So the products and the reactants, the coefficient 2, so I have 2 moles of water, and water is negative 286 kilojoules per mole. So the moles cancel out, plus, and then I have 2 moles of SO2, and SO2 is negative 297 kilojoules. So I did the products. And now the reactants, so H2S, so again it's 2 because the coefficient is 2, so 2 moles. And then H2S is negative 21 kilojoules per mole. And then that would be plus 0, because the O2 is 0. And again, note the units. And so this is actually, I was looking in my work here, the answer I get here, and again, this is really good to just go through the math. And this one comes out to be negative 1,124 kilojoules. That was the answer I wrote down for the first problem. So again, hopefully you noted how I changed the second problem. Again, I don't think it's a difficult process. And again, I'll have 1 or 2 of these on the Chapter 6 test. Okay. Let me go back and just almost done. So that is good news for those that are following along. Okay, so we've done this. This is the final way. Again, the appendix. Here's a reaction. If you guys Google this, a thermite reaction, it's kind of a cool, or YouTube it, go to YouTube and look up a thermite reaction. It's a reaction I've never done in all my years, but as you can see, it gets really, really hot. But I'm going to go through it here, and I'll have you guys finish this. This problem. I'll give you the values. But this, again, this would be a reaction that you guys would enjoy watching on YouTube if you went and saw a thermite reaction. So this is the reaction for thermite. So we have 2 aluminums plus Fe2O3 makes Al2O3 plus 2Fe. So let me sure we put that out right. Okay, so here are the values. Again, lone elements, aluminum are always 0. So aluminum is 0. The Fe2O3 comes out to be, when you look on the table, it's negative 826 kilojoules per mole. The aluminum oxide is negative 1,676 kilojoules per mole. And then the iron, again, something by itself is 0. And you guys could go through this, and when you watch this reaction, you can see it's very exothermic, but I'll let you guys work this. It comes out to be negative 850.4 kilojoules. So you guys can try that. Okay, almost done with this chapter. There's one problem I'm going to do in class on Wednesday, Thursday. Okay, guys, keep on working. We just got to do the best we can with what's going on. Have a good rest of your day.